The theory of how Poincare transformations affect state vectors describing massless particles is somewhat more complicated than the one that we have studied a while ago, that of massive particles. The complications essentially start from the fact that the little group for the standard momentum for massless particles happen to be slightly less better known than the corresponding little group for massive particles, which was just plain old SO3. But before we get into all that, let us first decide on what a standard 4 momentum would be, which we can use to describe massless particles. For that, we need our K mu, some standard 4 momentum which will have K squared, K upper mu, K lower mu equals 0, and K0 positive. So, the important point here is, whatever K0 is, this positive quantity kappa that we have written here, the magnitude of the spatial part of K mu must be exactly equal to that. That's what happens for all massless particles. So the spatial part here must be a 3 vector which has a magnitude kappa. By convention, and following Weinberg of course, we choose this 3 vector to be exactly along the third axis or the z axis. So the spatial part is just 0, 0, kappa, and so you get kappa 0, 0 kappa for our K mu. Let me warn you, as I have done before, that Weinberg uses the order 1, 2, 3, 0 to write his components. So Weinberg would write the same 4 vector as 0, 0, kappa. Small difference of no real consequence, but it might get confusing if you were to look up his book and see that he is saying something very different from what I am writing down. Now our first job, and one that will occupy us in this part, is figuring out what the little group for this K is. That is, finding out the set of all Lorentz transformations which will leave kappa 0, 0 kappa unchanged. Now note that if a particular matrix W, we will rather somewhat confusingly refer to W as both the whole set, that is the little group, or also a particular element of that group. I hope that will not confuse you too much. It should usually be clear from the context what we are talking about. Now a particular matrix W in this set, or particular Lorentz transformation in this set, will leave K invariant. Now if it leaves kappa 0, 0 kappa invariant, it's also obviously going to leave 1, 0, 0, 1 invariant. And for this section, we are just going to take K to be 1, 0, 0, 1. That's simply to make our notation and some of the calculations slightly simpler. So this is going to be our standard 4 momentum K for this section at least. Now, we know what W, a particular element of this little group, does to K. If you look at the W mu nu element, multiplying K nu and of course summed up over nu, we are using the Einstein summation convention obviously, you should get back K mu. Or if you think of this W mu nu, these W mu nu's as elements of a matrix W, here I must apologize for using the same letter that would also stand for the group. But again, from the context it should be obvious what I am referring to. We get WK equals K. So that's one thing we know about W. The other thing we know about W, of course, is that it has to be a Lorentz transformation. So it has to obey all the standard properties of a Lorentz transformation. So the question that we have now is, what is the most general possible matrix W that will satisfy WK equal to K? And we will answer that by first introducing 4 auxiliary 4 vectors, which we will write like we wrote K here as a column, T, the 4 vector, will have 4 components, 1, 0, 0, 0. So that's a purely time-like 4 vector. X, I hope you will not get confused between this and the coordinate X. This is a 4 vector, 0, 1, 0, 0. Y, 0, 0, 1, 0. And Z, 0, 0, 0, 1. In his book, Weinberg only uses T, does not refer to the other 3, except that he essentially uses the ideas that these other 3 would bring in. Now, the reason why we are looking at these four vectors is that if you look at the resulting 4 vectors when W acts on each one of them, that is WT, WX, WY, WZ, they are in a sense exactly what we are seeking, because these would provide the 4 columns of W, the matrix. There is no magic here or nothing relativistic or nothing quantum mechanical. This is simply the way matrices multiply. You could do this with any square matrix whatsoever. Here we are choosing to do it with our specific W matrix. So if we can find out WT, WX, WY, WZ, we are done. Now what helps us here is that W is not just any 4x4 matrix, it's also a matrix which depicts a Lorentz transformation. So one immediate result that we have is this 4 vector WT, if you use this to calculate its norm, you must get the same norm as the 4 vector you started with. This is simply the result that any Lorentz transformation preserves norm. And according to Weinberg's metric, this quantity is -1. So we know that the WT elements dotted with themselves gives you -1. Another very, very important result is this. WT mu, WK mu is of course T mu K mu. Lorentz transformations preserve inner products. And that of course is just -1. Remember, K is just 1, 0, 0, 1. When you take the 4-dimensional dot product of T with K, you have to multiply these two things, multiply by the corresponding eta, that is -1, and then multiply 0 with 0, 0 with 0, 1 with 0. Multiply them by eta 1, 1, eta 2, 2, eta 3, 3, of course, but that contributes 0 anyway. Now the reason why this last result is so important is that we already know what WK is. So we know that WT must obey this. WT mu, K mu is -1. Now given K has components 1, 0, 0, 1, that's K with upper indices. K with lower indices will actually have components -1, 0, 0, 1. What this result tells you essentially is this. You would take the 0th component of WT, multiply that by -1, and take the 3th component of WT, multiply that by +1, and add together. You are going to get -1. And that immediately tells me something about WT. It tells me that whatever the 3rd component is, the 0th component has to be 1 more than that. So, if we say that the 3rd component is zeta, the 0th component is 1 plus zeta. It doesn't matter what the 1th and the 2th components are as far as this particular relation is concerned, because K has zeros in the 1th and the 2th positions. So, as far as inner product with K is concerned, those terms contribute nothing. So, just to complete this, let's put in numbers alpha and beta here. Any 4 vector of this form is going to satisfy this relationship. However, we have one more restriction on Wt, as we have already stated. Wt must give you -1 when dotted with itself. Now, when you dot this vector with itself, what you get is -1 plus zeta whole square. Remember, the dot product is the 4-dimensional dot product. Minus x0, y0 plus x1, y1 plus x2, y2 plus x3, y3 plus alpha square plus beta square plus zeta square equals -1. Now this, of course, expands to -1 plus 2 zeta plus zeta square, and the zeta square cancels with this zeta square, and you are left with a very, very simple result that zeta, this component, can be uniquely written down in terms of alpha and beta. Beta is simply alpha square plus beta square by 2. So I will keep on writing zeta in what follows, but you have to remember that zeta is not independent. Zeta is always alpha square plus beta square by 2. So what we have here is a general form for Wt. We do need the general form for Wx, Wy, Wz to complete our quest for the most general possible W, the most general possible Lorentz transformation matrix that will keep 1, 0, 0, 1 invariant. So let's figure out exactly what else we know. In fact, we can immediately write down Wz, the last of the 3th column. Why? Because Z is simply nothing but K1001 minus T 1000. So this is Wk minus Wt. We already know what these two things are. We know that Wk has to be K, and Wt, we have just figured out the most general possible form for that. And so immediately we can write down Wz by subtracting from 1001 this quantity. And that immediately gives you minus zeta, 1 minus zeta, minus alpha, minus beta. Once again, let me warn you that if you look at Weinberg's book, his general W matrix looks different from what we are doing here, simply because his ordering of the rows and columns would be different. So we have got two of the columns, Wt, which gives me the 0th column, and Wz, which gives me the last or the 3th column of W. What about the other two columns? Well, for that, we again can make use of exactly what Lorentz transformations tell us. One of the first things you know about Wx, for example, is that if you were to dot it with itself, the result would be the same as the original 4-vector x dotted with itself, and because of the choice of matrix which Weinberg has made, this is going to be +1. So that's one thing we know. Another thing that we know is this. We are following the same lines of argument that we used for Wt. If we take Wx and dot it with Wk, you get x mu, k mu. But if you remember, k is 1001, whereas x is 0100, the dot product is just 0. So Wx upper mu with k mu, this is what Wk really is going to vanish. So what does this tell me? It tells me the following. If you think of the 4 components of Wx as, say, P, Q, R, S, then when you dot it with 1001, you must get 0. That immediately tells you that P minus S, which is the dot product in this case, is 0. So P and S have to be equal. So what we have essentially is P, Q, R, P. This is the most general form for Wx. In fact, you can easily figure out that this also works for Wy. The most general form for Wy will be P prime, Q prime, R prime, P prime. where the numbers, of course, could very well be different from these numbers. Now, this only uses the fact that Wx is orthogonal to K, but you also have other things which you can use. For example, Wx's inner product with itself is 1. If you use that, you get minus p square plus q square plus r square plus p square equals 1. And that immediately gives you q square plus r square must be 1. But we have a simpler piece of information that we can make use of. Wx's inner product with Wt has to vanish. We already know what Wt is. Wt is 1 plus zeta, alpha, beta, zeta. So what you get from this is minus p into 1 plus zeta plus q into alpha plus r into beta plus p into zeta equals 0. And you can simplify this a bit by cancelling out p zeta here, and that immediately tells me that p is not an independent quantity. P is given by q times alpha plus r times beta. Now this actually works both for Wx and Wy. Now we can go on and write down the most general possible form for W by using this. It is pretty straightforward. Simply because q square plus r square equals 1, I could write q and r as cos theta and minus sin theta. Why minus? That's because it's going to make the final form look better. And then P would of course end up being alpha cos theta minus beta sin theta. So that will give me my column Wx. For Wy, you will get exactly similar things, except for the additional demand that because Wy has to be orthogonal to Wx as well. Since x and y originally were orthogonal, that will relate the two thetas in the two columns to each other. And you can write down the most general form just by using the fact that one theta has to be related to the other one by a very simple relation. In fact, what you will get is Wy will become alpha sine theta plus beta cos theta as the 0th element and the 3rd element. And the 1th and the 2th elements will be sine theta and cos theta respectively. And that gives you the most general possible W. However, and that of course is exactly what we are seeking. However, what we really need to do is understand the structure of W in order to be able to figure out what its representations are. And this particular form of most general W is a bit too complicated to understand its general properties easily. So what Weinberg does is something very clever. He chooses a particular value for Q and R and for Q prime and R prime to get not the most general possible matrix W in the little group, but a specific subclass of those matrices to begin with. So let me show you what Weinberg does. What Weinberg does is the following. He chooses a special set of values for Q and R and Q prime R prime and uses that to write down a subclass of W, as we said, with elements given by the following matrix elements. 1 plus zeta, alpha, beta, zeta, this 0th column, and minus zeta, minus alpha, minus beta, 1 minus zeta, have already been fixed. Remember, zeta is alpha square plus beta square by 2. And for the 1th and the 2th column, what he does is the following. He chooses 1, 0 for Q and R, which of course makes these alpha, and 0, 1 for Q prime R prime and makes this beta. You can easily check that this column and this column are also orthogonal to each other in the four-dimensional sense. So this is a specific type of little group element for K. Not all of them. But let me just point out what it does next, and that's the clever part. What he says is the following. S alpha beta, what does it do? It definitely takes K to K. That's what being a little group element means. And takes T to whatever WT takes, right? Because every W element corresponding to the parameters alpha and beta will take T to this 1 plus zeta alpha beta zeta. That's what we have already established. Therefore, S inverse alpha beta, this matrix, times W, what will that do? If it acts on K, it will take it to K. It is one of the little group elements, of course. Whereas W, of course, takes K to K, and then S inverse will take K back to K, which means it doesn't change at all. On the other hand, this takes T first to WT, but S alpha beta takes T to WT as well, so S inverse alpha beta will take WT back to T. So S inverse alpha beta W will keep the vector 1, 0, 0, 0 unchanged. So it's a Lorentz transformation, being a combination of two Lorentz transformations, which is a member of our little group, but which also keeps T unchanged. Because it keeps T unchanged, it has to be a rotation. But now, what is the rotation which will keep 1, 0, 0, 1, that is K, unchanged? The answer is it has to be a rotation about the z-axis. So this quantity S inverse alpha beta W cannot be an arbitrary Lorentz transformation. Has to be a rotation about the z-axis, which we are going to write as r theta. And of course, the corresponding matrix will be 1, 0, 0, 0 and cos theta minus sin theta, sin theta. So what we end up with is this statement, that the most general possible element of the little group W, which has parameters alpha, beta and theta, will be given by S alpha beta times R theta. If you were to multiply out S alpha beta with R theta, you will actually get the form that we have written down here, which, as we argued, is the most general possible form for W, given parameters alpha, beta and theta. So we have established several things here, and the most important one for us is basically W is a 3-parameter group. 3 independent parameters alpha, beta and theta are required to describe completely a given matrix W in the little group. We will next try to identify this group. What this means is, we will try to find a better studied group which is for all purposes of group-like behavior identical to this one. In the jargon of group theory, we are looking for a quote-unquote familiar group that is isomorphic to this particular one. It turns out that this better known group happens to be ISO2, the group of inhomogeneous rotations in 2 dimensions. That is, the group of translations and rotations in a plane. We are going to explore this and its properties in the next part of this lecture.